You know the feeling, right? You drop a hog rider, they counter with a skeleton army, and it all just happens. It's instant, it's perfectly in sync, it just works. But have you ever really stopped to think about the absolute engineering madness happening behind the scenes to make that one moment possible for millions of people at the same time? So, how does that one single tap on your screen translate into a perfectly synchronized, totally lag-free battle? Well, we're going to peel back all the layers on the incredible tech that powers this thing. This is the real, deep dive engineering story of how that one tap connects you to the entire world. All right, here's the plan for our journey. We'll start with the synchronized simulation, then move to the global server architecture. After that, we'll look at the real-time data layer, then get into the nitty-gritty of taming the Java virtual machine. And finally, we'll put it all together. All right, first stop on our tour, the synchronized simulation. The motto here is sending less is more. And this all comes down to tackling the single biggest problem in any mobile game, bandwidth. I mean, your phone's connection is pretty good, but it's not magic, right? So how do they possibly manage all that on-screen chaos without melting your phone? Think about it. You could have 30, maybe more, units on the screen at once. If Supercell tried to send you the position, the health bar, and the animation for every single one of them multiple times a second, well, your data plan would just evaporate. The lag would be insane. No way that would work. They needed a much, much cleverer way to do this. And this is it. This is the secret sauce. It's called a deterministic lockstep simulation. It's a bit of a mouthful, but the idea is brilliant. Instead of streaming the whole game to you, the server only sends the inputs. So your phone and your opponent's phone are running the exact same copy of the game, like two perfectly synchronized clocks. The server's only job is to say, hey, player one just dropped a knight right here. And boom, both of your phones know exactly what to do. The amount of data they have to send is tiny in comparison. So here's another thing that might blow your mind. The game isn't actually continuous. It's not a smooth flow of time. It's way more like a movie, right? It's made up of thousands of individual frames. The server moves the game forward in these tiny little discrete steps. They call them ticks. And as long as it processes those ticks fast enough, you get this perfect illusion of smooth, nonstop, real-time action. And every single one of those ticks is like a perfectly organized little 3-act play. First, you've got input processing. The server just listens and collects all the commands from both players. Then, Act 2, game logic. It takes those inputs and advances the simulation forward by just one step. Finally, output processing. The server tells both players what the result was. And this whole cycle repeats over and over at an absolutely blistering speed. Okay, that simulation logic is genius for sure, but it's completely useless if your commands take forever to even get to the server. So the next big question is, how does Supercell make sure a match between someone in Tokyo and someone in Brazil is actually fair and lag-free? That's all about conquering latency across continents. So when you're building a global game, you basically have two main choices. You could go fully centralized, stick all your servers in one spot. Super easy to manage, but terrible for players on the other side of the planet. Or you could distribute your game servers everywhere, which gives players low latency, but is a total nightmare to deploy and keep consistent. And what Supercell did is pretty clever. They chose a hybrid model, centralized data, but distributed logic. What does that mean? It means the actual game you're playing runs on a server that's physically close to you, which is why it feels so fast. But your account, your cards, your gold, all the important stuff, that lives in one central master database. It really is the best of both worlds. And to solve that last mile problem, the connection from you to their closest server, they use some really cool AWS services. Think of AWS Global Accelerator as a private, super fast highway for their game traffic. It bypasses all the slow, congested public internet. And then you have AWS local zones, which are basically mini data centers plopped down right in the middle of major cities. This gets the compute power as physically close to you as humanly possible. We're talking single-digit millisecond latency. Okay, but a game like Clash Royale isn't just about the battle, right? It's the clan chat, your friends list, who's online, card requests, all that social stuff. And that social backbone is a totally different, but just as important, real-time data problem. So to handle all of that, from a simple chat message to checking if your friend is online, the engineers came up with this beautifully simple yet super powerful data model. It's basically a hierarchical key value store, which looks a bit like this map of string, string. Just think of it like a digital filing cabinet. You've got a drawer, inside that is a folder, and inside that is a piece of paper. That might sound a bit abstract, but it gets crystal clear when you see an example. So for a chat message, the top-level drawer is the room ID. The folder inside is a unique ID for that specific message, usually based on the time. And then the paper inside that is the message itself, like "Hi there." With this one simple pattern, they can model almost any social feature they can dream up. It's incredibly flexible.
And this quote from Edvard Fagerholm, one of their server engineers, just nails the philosophy. We wanted to build one thing, not many. I mean, think about that. Instead of building a custom system for chat, another for friend lists, another for presence, they built one powerful, abstract system that could do it all. That is just a masterclass in smart engineering.
Now, to power a system like this, you can't just use any old database. You need something special. You need something that can handle a ridiculous number of small writes with super low and, most importantly, predictable latency. And for that, they went with ScyllaDB. It's a NoSQL database that's basically purpose-built for this exact kind of workload. Okay, now we're going really deep down the rabbit hole. We're talking about the game servers themselves, the very heart of the system. And here's the shocker. They're written in Java. Now, for anyone in game development, that's a bold choice. You could even say it's controversial for a real-time game, and it creates some absolutely massive engineering challenges they had to overcome. And here's the central problem. It's a huge paradox. The things that make Java amazing for enterprise applications are the very things that make it a nightmare for a real-time game server. You've got the JIT, or just-in-time compiler, which is supposed to speed up your code, but if it makes a bad prediction, it can cause a de-optimization, a huge performance drop. And then there's the infamous garbage collector. It's great that it manages memory for you, but it can decide to pause your entire application at any time to clean house, which for players just looks like a massive random lag spike. Let's walk through exactly how this can bite you. So the JIT compiler is running, it's watching how the game code runs, and it makes some smart predictions to optimize things. But then, a new game mode drops. All of a sudden, players are doing totally different things. The compiler's predictions are now dead wrong, which triggers that de-optimization we talked about. The server literally has to pause, recompile the code, and in that moment, everyone connected to that server experiences a huge lag spike.
So what about that other big problem, the garbage collector? Well, they solved it by swapping out Java's default collector, which is called G1GC, for a much more specialized one called ZGC, or the Z garbage collector. And this chart says it all. Look at the drop in the percentage of late ticks. ZGC is engineered for one thing above all else: incredibly short, predictable pause times, often under 10 milliseconds. And for a real-time game, that predictability is absolutely everything.
Okay, we've looked at all the pieces in isolation. We have the clever simulation logic, the super fast global network, the flexible real-time data layer, and the highly tuned Java engine. Now, let's put it all together and trace the entire journey of one single tap. Here we go. You tap your phone to deploy a card. That input immediately gets routed through the AWS Global Accelerator to the nearest game server. That server, running Java with the low-latency ZGC, grabs your input. On its very next tick, it processes the command. If something social needs to happen, like a clan notification, it'll ping the central ScyllaDB cluster. And finally, the new game state is broadcast back to you and your opponent. And all of that happens in a fraction of a second. And let me be clear, all this deep, complex JVM tuning wasn't just some academic exercise. The results were absolutely staggering. They saw a more than 5-fold increase in the player load a single server could handle. Think about what that means: way fewer servers, much lower costs, and a massively more efficient system, all while making the game better for us.